Hi, good morning. All of us have been reading about Chandrayaan and Aditya launches and all that, and how it took so long to go there, and multiple orbit race maneuvers and stuff like that. So I thought I'll spend a few minutes talking to you about satellite orbits, and with reference to especially Chandrayaan and Aditya, which is towards the sun. Basically, let's start from getting going into an orbit. What do we mean by going into an orbit? Earth's gravity, as we all know, is approximated as giving a constant acceleration at the surface of 9.81 meters per second square. It quickly reduces as we move away from the sphere of the Earth. Imagine launching a succession of rockets upwards at increasing velocities. At initial low velocities, they just go up a certain height and fall back down. But there comes a velocity with which you throw, they escape from the Earth's gravitational pull and actually would break free. Since it breaks free from the Earth's gravitational field, it's called the escape velocity. And of course, it depends on the gravitational forces of that particular planet. So eventually, it depends on, it's different for different planets. For the case of Earth, the escape velocity is roughly 11.2 kilometers per second. Now, let's look at the Earth's curvature. So Earth, as we know, is spherical and the surface is curved. So we need to be able to estimate the curvature of the Earth at any one point. The Earth's radius is approximated to be 6,371 kilometers. Of course, it differs at the poles and at the equator, but let's take this as a number, average radius of 6,371 kilometers. And of course, this is based on numbers I got from Wikipedia. Circumference of that Earth with that 2 pi r calculation, you'll get around 40,030 kilometers roughly. So we wish to find the height, which is the drop in curvature over the distance of certain d. Now, all of us have studied in school that if you stand near the shore and the ship starts from the shore, it starts disappearing slowly, and after some time, you don't see the ship at all. That's because the Earth is curved and the surface kind of recedes away from us as we move, it moves away from us. Using the circumference, we find that 1 kilometer on the circumference has an angle which you can compute by 2 pi by 40,030 kilometers, and roughly is 157 radius. The angle A is then, from the figure you can see, you can compute uh, as 0.00157 times the distance d. Okay, so the derived formula, this is for 1 kilometer, and the derived formula is valid for any distance. So let's look at what happens. I want to assume that the height, the drop in height is around 5 meters. I'll come to as to why I'm talking about 5 meters. Then for a distance of 8 kilometers, the Earth's surface curves away from us by about 5 meters. So now let's look at another analogy. Let's say you throw a baseball or a cricket ball. No matter how fast you throw the ball, it falls down at the same rate. Only the force other than the drag is gravity, and it falls down at about 4.9 meters per, in a second. This comes from the fact that the height drop is half of gt square, g being 9.81, t is 1 second. In 1 second, it falls about half of g, that's roughly 4.9 meters. So Earth's curvature is such that it dips away from us about 5 meters after 8 kilometers, as we saw in the previous calculation. You can see only the top of a 5-meter tall tower at a distance of 8 kilometers. Remember the vanishing ships as they sail away, which I talked about earlier. So if you throw at about the ball at a speed of about 8 kilometers per second, which is of course phenomenal, there's no way you can throw at that. Suppose you can throw it at that speed, it will keep falling because at the rate of half a meter per second, but it will never touch the ground as the ground itself is curving away from that. So essentially, the ball goes into an orbit. So what I'm trying to indicate here is if the circumferential velocity of an object is around 8 kilometers per second, then it basically goes into orbit. How do you go to the 8 kilometers per second is a different topic. We are not going to talk about that today. So the same ball analogy, if you look at this figure on the left, depending on what speed you throw. Initial low speeds, it'll fall down to Earth. Okay, slightly higher speed, it'll go into an elliptic orbit. Slightly higher speed, it'll go into parabolic, and finally, it'll go into hyperbolic orbit. Those are just incidental. This is a picture I got from the open domain. It's not something I created. So it depends on the throw velocity. So different satellites, you have to be placed in different orbits, uh, so that their periods going around the Earth is important to us. For example, if you are looking at a geostationary satellite, which means that the satellite is observing the same part of the Earth all the time throughout the year. It's called a geostationary satellite. It's usually used for communication purposes, like INSAT 1, 2, 3, and all those. And this is roughly to be at the altitude of 36,000 kilometers away from the Earth on the equator. Because if you don't have a rocket which is powerful enough to directly place it at that orbit, you first place it at what's called a transfer orbit, and that could be roughly 180 kilometers at one point, perigee, that's nearest to the Earth, and 36,000 kilometers at apogee, furthest from the Earth. So this is what is the transfer orbit from which we need to get into a circular orbit of 36 kilometers. That's what I want to spend some time talking to you about today, how that is done. This is another way to look at orbits. One of the simpler ways I explain about Earth's curvature, this is using the centrifugal force. So any object going around a circular path has a centrifugal force which is mv squared by r, m being the mass of the object, which in this case could be a satellite or a planet or anything. And v is the circumferential velocity, and the r is the distance away from the center in which it is going around. So in the case of a satellite for Earth, it should be the balancing weight should be mg. So it will be mg equal to mv squared by r. M cancels out. And from that, you can calculate, as I have shown here, roughly the velocity you need to be traveling at is 8 kilometers per second, or 28,800 kilometers per hour speed, which is, of course, a phenomenal thing for the object's centrifugal force to be balanced by the gravitational attraction of the planet. This, of course, changes if you're going around on the moon. It will be much less than this. As I said, it depends on the local gravitational constant. Now, there are different types of orbits. So, to orbit a spacecraft on Earth, it must be launched uh, to an elevation above the Earth's atmosphere and accelerated to orbital velocity. Why above the Earth's atmosphere? Because when the atmosphere is present, there is drag, and when there is drag, it will slow down the velocity. As the velocity slows down, the orbit radius will start dropping, and eventually the satellite will fall down to Earth. So you have to place it at least about 100 kilometers above the Earth, so that the gravity or the atmospheric drag is minimized. And it also needs to have that orbital velocity of 8 kilometers minimum for it to be able to go around the Earth without falling. The most energy efficient orbit is achieved when a spacecraft is launched in an eastward direction from a site near the Earth's equator. That's because the Earth is rotating, and at the surface velocity at the equator is about the highest velocity. And if you're launching towards the east, you're getting a free ride because the Earth is rotating at roughly about 1,400 kilometers per hour. So you get that additional speed. It's like if you run at a certain velocity, but you jump off from a moving bus, continue running, your velocity will be much higher. Of course, you may end up falling down. That's a different issue, but the velocity of the bus will add to your running velocity. Similarly, the rotational velocity of Cape Canaveral, this is, as I said, figures from NASA, and most of the US launches are from Cape Canaveral in near Florida. At that point, the Earth's rotational velocity is about 1,471 kilometers per hour. So if you launch it towards the east, you get an additional free ride of about this. And then you need to have only a lesser velocity addition. Just an aside, this is for civilian launch vehicles. Now, if you get into a war and you have to launch a missile, you can't always be launching towards the east because you may or may not have your enemies on the east. You may have enemies on the west or the north or south or whichever direction. But for launch vehicles, civilian launch vehicles, you launch towards the east, especially if possible from the equator. We are that way a little benefited because we are closer to the equator than the Cape Canaveral. Bangalore being about 13 degrees north, and Sriharikota being a little northern than that. So if you look at any orbit, Kepler designed that the stablest orbit would be elliptical. Okay, elliptical orbit means, let's say this is the sun is somewhere, the earth is here, and it is a flattened circle, the nearest point being perigee, the farthest point apogee, and the eccentricity is the formula here. Right now, the reason I'm showing this figure is because I'm going to use this figure eventually to show you how Chandrayaan and Aditya satellites depend initially are put into this kind of orbit, elliptical orbit. From there, the orbit is changed towards whatever orbit you need through a series of rocket firings. So let's look at an old ISRO press release, which says the satellite was placed into a geostationary transfer orbit with a perigee of 180 kilometers, which is the nearest part towards the Earth, and an apogee of 36,000 kilometers, and an inclination of 19.3 degrees. And this is going to be a geostationary satellite, which means that it has to have a circular orbit of constant radius distance away from the Earth of 36,000 kilometers and above the equator. All geostationary satellites have to be above the equator. Anywhere else, it won't be geostationary. That's another point we need to remember. And as I said, India does not have that kind of a very, very powerful rocket which can directly take it up that and place. It places it first in an elliptic orbit, and then slowly it transfers it into that orbit. How that is done is what we are going to talk now. So rockets sending payloads to geostationary orbits drop off the payload, which is the satellite, in the transfer orbit. Halfway points en route to the satellite's final position. From the transfer orbit, the satellite conducts engine burns to circularize the orbit. Remember, the one point is already 36,000 kilometers. The other point is very close to the Earth. We need to circularize the orbit, meaning we need to increase the perigee from whatever the 180 kilometers the ISRO's GSAT was to finally 36,000 kilometers. How this is done is explained in the next slide. So if you see a rough cartoonish picture here, which I have shown, the initial orbit is this elliptical orbit where you have the Earth here and you have the apogee point here. Now, there is a slight difference between what was done for GSAT and what was done for Chandrayaan and what's going to be done for Aditya. Here, in this case, what is done at the apogee, the velocity of the satellite is the lowest because it's the furthest from the point of attraction. So at this point, this is what you want the final arbitrary the orbit location you want to be. So a small burn time is used, a rocket is fired. So what it does is it increases the perigee, let's say from 180 to 5,000 kilometers. So now it's an ellipse, 36,000 kilometers apogee, 5,000 kilometers perigee. These numbers are just for explanation. They don't have to be exact. Then one more firing is done. So that places it slightly closer, maybe 28,000 kilometers. So on multiple firings are done. Finally, the orbit becomes this circular. Okay, and that will be 36,000 kilometers. So why this is done is, as I said earlier, we just do not have a powerful enough rocket to place it there directly. Plus, you can use a rocket which is a lesser power, which means lesser fuel burn, less cost and economical. Basically, you're trying to maximize the return on the investment. So this is how it's done, and of course the method has a lot of benefits. This is done in multiple stages. Because of this, it takes a few days or sometimes weeks for it to be finally parked at that particular station where it is supposed to be there. So let's look at another press release. This is a slightly older one from ISRO again, Chandrayaan 2. What we have now is Chandrayaan 3 landing, which was touched down on the moon. This was the previous one. Was launched into an initial Earth orbit with a perigee of 170 kilometers and an apogee of 40,400. This is more than 36,000 because we want this satellite to actually move away from the Earth towards the moon. So the apogee point is much higher than what was used in GSAT launch. So it's slowly making its way to the moon. This is a press release. The engine is not powerful enough to do a single transfer injection. So instead, it's taking advantage of what's called the Oberth effect by making a burn each time it reaches the perigee. Boosting to a higher apogee each time, it will eventually go to the moon. So the explanation what they have done is in the next slide. Now the same initial orbit ellipse, the satellite is placed in this ellipse, and the apogee is 40,000 plus. See, in the previous maneuver, the rockets were fired at the apogee point, the furthest point, because they wanted to circularize that. In this case, they want the satellite to leave the Earth's atmosphere and go towards the moon. So the firing is done near the perigee point. Perigee point where the satellite's velocity is the lowest, and if you fire the rocket here, what it does, it increases the apogee distance. Let's say from 40,000 to 60,000, 60 to 70,000, and then finally it completely escapes from the Earth's velocity and goes towards the moon. So this is one of the maneuvers it's used, and it has used this because we don't have a big enough launch vehicle to uh, reach the escape velocity straight away. And this is, of course, a smarter way, more economical way, lesser fuel burn, and easier to accomplish. Advantages, of course, energy conservation permits satellites to change their trajectory with lesser fuel burn, and this extends the mission's lifespan. So every satellite has a certain amount of propulsion material available in it to keep what is called station keeping, to keep it in the same place. Because of disturbances, it starts moving a little bit, so we need to be correcting it continuously. So for that, there is a residual fuel present, propellant present. Now, if I have more propellant present, the satellite life is longer. And you must have heard, some of the satellites land about 5 years, 5 years, 6 years, sometimes a little longer. So more fuel you save and put it on the satellites, the better, longer life you have. And lower power launches. This is particularly useful for missions like Chandrayaan and Aditya. Of course, we are constrained by the lack of very powerful rockets, but we have to use whatever we have. So that's one of the reasons why this kind of complex trajectory changes maneuvers can be used to perform whatever we need, including altering the inclination of an orbit or sending a spacecraft to the moon, as it was done in Chandrayaan and now in Aditya. Disadvantages, it takes longer time for the satellite to reach destination. You must have read, the Russian rocket took about 4 or 5 days to go, whereas our rocket took much longer. The Russian launch was much after the Chandrayaan launch from India, but still it was closer to the moon than the Chandrayaan because they are the space pioneers. They have much more powerful rocket, but we have to do what we have with what we have got. That's how it thinks. So I'll stop here, and if you have any queries or comments, please send it to me and the email ID I have seen in the beginning. I've shown you in the beginning. I'll be happy to address. Thank you for listening to me.